All right, hi everyone. Welcome back. I hope everyone had a good spring break. Today is a really exciting class because we're going to talk about actual real-world applications and the kinds of things that you can all do for projects. So as I was just saying before I started the recording, the idea of today is we're going to have 15 to 20 minutes of just us talking to you about these are the kinds of things you can do per like subfield of physics or astro. Like these are the kinds of things people look into and use. And then, and that's the only bit that we're going to have recorded. After that, we'll stop the recording, and we're going to either all stay in the main room or go into breakout rooms, whatever we prefer at the time, and talk about specific things that you can do for projects. Ideally, everyone should come away from this lecture, if you're here live, with a project idea. If you're watching this later, please reach out to one of us, let us know, and we'll set up a time where we can talk through like what are the things you're interested in maybe doing for a project. So we're going to say, we haven't set a deadline for the project proposals yet, but I think giving about a week for that is reasonable because like what we want is pretty short. We just want like a 1-paragraph description of like what you'll do in some sense of like you've thought through how you're going to implement it. So it's not terrible to do. And the projects themselves are also not supposed to be like terribly complicated either. They're like about a homework's length. Like about as much effort as you put into any one homework for this class would make a good project. And we're going to talk about what could be a good project in a minute. Any questions before we get started? Okay, seems like no. Oh yeah, and one more thing is so that everyone has a little more time, and because we've been just lagging just a little bit on the homeworks, we were originally going to have 5 coding homeworks. We're now just going to have 4. So what I previously released as homework 4 is now going to be homework 5, and I'll have it due, I think, in 2 weeks from today, after I'll be done with all the relevant stuff in lecture. And now what homework 4 is it's the project proposal. So hopefully that should take some of the load off, because I know we've had like a bunch of late submissions, so we want to make this like as accessible and let everyone do like what they're actually interested in these projects. Okay, so starting. Wait, sorry, in the screen share, do you see the little sidebar? Because I do not want that. I'm just going to do this. Yeah. Okay. So there's a bunch of like specific libraries and frameworks that people use in real life research. So probably the biggest example is AstroPy in like anything astronomy related. There's a bunch of like common applications to astronomy. Like a really common data type is a FITS file, and I forget exactly what FITS stands for. Maybe someone in the chat will remember. But it's really common to use for like spectra and images and things like that. And so it made sense to just have a common library with like shared assets for dealing with that kind of data. So that's astropy.fits. And so they put together a bunch of these use cases that are common to a lot of astronomy, and they made it into this Python package, astropy. And similarly, I know a little less about it. There's Root, which is a framework released by CERN that I'll talk about in a minute when we get to that slide. And GNU-Radio similarly, I was going to talk about that in a minute. So often research, like getting started with research, involves sort of learning to use these things specifically. It's not just I know Python, it's I know how to use this specific library. I know my way around astropy a bit. How you get there can be, you have someone show you, like usually like a research PI or someone is going to like talk you through like the basics of it, or wait for us to tell you how to figure it all out from documentation. Also, I'm not going to open my messages right now just for fear that like it's going to show up on the main screen just in case it's a DM or something. So if you've got something you want to DM, send it to Alad and he can deal with it.
That stuff.
Yeah. Okay. So there are ways to learn these like slightly more specific things about coding. So we're going to run through a quick survey of like some subfields of physics and astro and how they use computation. We're a little biased towards what we know well, So we'll have more details on some things, less details on the others. And there's some subfields we just can't touch upon. And also, I think we both don't think that physics and Astro have like really good unified code bases in the way that like sometimes we want them to. And that's something that I hope will change, and that like at least in my future research I hope to change. But for now the situation is like a lot of code is going to be common and is going to need to know frameworks. A lot is not and is going to be more ad hoc. So you have to be sort of ready for both of those modes. If there's a thing you're interested in and we don't touch on it much, or we're like, yeah, we don't know a ton about this personally, bring it up in the open discussion period when we're done. We'll talk about it then. And we can also I can also definitely connect you to friends who actually do research in whatever area you're interested in, and they can maybe give you a few more pointers on how to get started with any super specific questions. But for coding in general, yeah, let's talk about that. Okay, Ada, do you want to go for it?
Yes. So Root is a package that CERN developed, and basically the accelerators at CERN generate petabytes and petabytes of data every day when they're running, just from all the different sensors. So Root is basically a data framework they developed to let you efficiently store, manage, and then run queries to do science on that data. So if you've got like some radio data, filter it. If you've got something, just like extract the science out of the data and do it efficiently across like potentially, that data might be split across a couple hundred servers that all are storing it in different places. And for, massive data sets, you want to operate on it in parallel. So Root provides routines to let you easily do that. And then GNU Radio, which is something I use a bit more in the research I do at LBL, is basically it's a set of tools. It has applications across also Root also has applications in not particle physics. It's not really particle physics specific. Same thing with GNU Radio, but it turns out that a lot of particle detectors are basically just like really fancy radios with different types of antennas. If that means something more fundamental about the world of physics, it's up to you to decide. But basically, a lot of things are radios, and GNU Radio is basically a tool that lets you build. And so, like, instead of having to get a physical filter and put it on your radio, and a physical X and a physical Y and a physical Z and put it on the front of your radio, you can just capture raw radio data and then you run it through GNU Radio, and you can build various different software configurations of filters, and you can add some noise, and it lets you simulate like how a radio is going to operate and also process your data. So it's very handy. Those are two tools that I've encountered a couple times. Yeah, neither Ditya and I are atomic, molecular or optics physics people, but two things I've heard of are ARC, which basically helps you like solve the Schrodinger equation for some atom, and we'll tell you the energy levels and how those split and stuff. And then ASE is like a little bit, it's kind of like I forget what ASE stands for, but it's a tool that basically like lets you assemble atoms into a molecule and tries to numerically solve how they interact and stuff. So yeah, I haven't used either of those, and I'm not an atomic physicist, so I don't know a whole lot about them, but I've heard of them.
All right. So for exoplanets, there is actually like a thriving like open source set of packages that you use. Most of them are Python, unfortunately, but I'm working on it. So one really good thing I think about exoplanet science, about like most science I've encountered really, but especially exoplanets, is a lot of the data is open source. Like you can go look up like the data for like every single confirmed or suspected exoplanet out there. Candidate exoplanet, suspected is like something out of Among Us. Yeah, on here, the NASA Caltech Exoplanet Archive. And it's really good. It just lets you like, you could just load up like a massive table of all of these exoplanets, and you can look at like all kinds of data, like here are the periods and radii and the uncertainties on those, and like 50 different parameters you've never even heard of. And there's a lot to work with and do analysis with. On top of that, there are packages. While the like raw pixel by pixel data from surveys is like too massive to put online, there are a lot of packages out there that will let you get like slightly cleaned like subsets of this data. So one really good one is Light Curve, spelled with a K, to be cool, which lets you analyze transit data, which is like for all the missions out there that are looking at stars hoping the planet will transit them, like the actual like brightness over time curves that you get out of that. Another one I've heard of is RADVEL for fitting radial velocity, which is the other main mode of looking at exoplanets. And there's a bunch of other packages that do MCMC, which is a statistics thing that I'll talk about in a couple of weeks that's really generally useful, that have all been collected into this planet, just handily called Exoplanet. So those are some things you might want to check out. Also, like everything to do with astronomy, AstroPy is a really useful resource for like loading from FITS files or dealing with, astro-relevant unit systems and things like that. Okay. High energy astrophysics also has like a massive amount of data that's pretty freely accessible and useful tools. So there's XSELECT and XSPEC. So high energy astrophysics is to do with things that you observe at like X-ray wavelengths and that kind of thing, which is where the X comes from, I would assume, and things like supermassive black holes as well. A lot of really cool objects that are the kind of things that like get people into astro. One thing that I've heard about quite a bit is DS9, which is sort of a specific visualization software that's really good to know. Like if you go into like a research group or something saying one or all of these, that might be like a really good thing to have under your belt in terms of you already know like a lot of the basic skills and are able to like hit the ground running with that. That's true in general of all of these, of course. But yeah, there's a lot of like, I don't know if they're all open source. Some are definitely open source, but a lot of freely accessible tools out there that you can learn and get a leg up in like getting research positions if that's where you are. Okay, and cosmology. The only like unified thing I could find really for this is AstroPy's cosmology module, which lets you do calculations for like, I'm going to make a model of a universe that's curved in this way with this parameter, and I'm going to do some calculations of like what's the distance between those two things relative to what it is in a flat universe, that kind of thing. But also one specific thing I looked into here is cosmic microwave background observing missions. There's like dozens and dozens of these. Many of them are based out of Berkeley, and all their raw data and like a whole lot of their tools are on NASA.gov over here. So throughout Astro, you see the unifying thing of NASA is very like generous with their data. So I'd say a problem here, maybe it's just a function of not having looked into it as much, but I think exoplanets definitely have the best like unified infrastructure of open source packages, and the rest are generally not as good, and you're going to be dealing with like ad hoc things or legacy code specific to a project, things like that. But these are some starting points. Okay, so with all that, project ideas. There is like a few different ways you can approach the project for this class. One of them is build off something that you liked from the class itself. Alad showed off a ray tracer in the very first lecture. You could build a Julia version of that and get the benefits of just-in-time compilation of things being written more naturally for science. There's a whole lot of stuff that I really wanted to include in what is now homework 5, like better solvers or a more efficient setup that I can explain like as needed. For the n-body integration problem, but I wasn't able to because that homework was like big enough as it is, and I do need to keep in mind that like all of you have lives. But if you want to dive in, I'm like more than happy for you to do that. Like this is a really great thing, and it's like really relevant to a lot of science of like galaxy simulation and planetary system simulation and simulating even just like charged particles at a microscopic level. A lot of it comes down to efficient ways to solve the n-body integration problem. Another thing you can do is take something that you've done before in coding. Like if you took Physics 77, take something that you really liked from that and make it faster, run it on Alad's server. You can revisit the Ising model in higher dimensions. I'm going to talk in a couple of weeks about MCMC and machine learning. Also, Alad, let me know if those chat notifications are something I should stop for. Yeah. Like I'm going to be talking about MCMC in a couple of weeks, and one of the really cool applications of that, which we already sort of did in homework 1, is the Ising model of like ferromagnetism, and in general, like how spins line up with temperature. And that has some really interesting like emergent properties that come up once you go to more than one dimension. That would be really cool to look into. I might use this in lecture as my example, but even if I do, there'll be a lot for you to do to like add on to it for a project. And then the last one's Alad's idea of, we've made the point a few times in this class that languages matter less than ideas. So to reflect that, pick a new language, do something with it that's like naturally done in that language.
Yes, like if you picked like Go, for example, is designed for parallel processing. So if you picked Go, you might maybe implement an M-body simulator, but do it with explicit parallelization in a way that's kind of more difficult to do in Julia or Python.
Part 2, you can pick something. I suspect this one's going to be more common. Pick something in physics or Astra that you like, write a bit of code that does that. So we're going to get into that like in a minute, but here's some ideas for like what that could be to start with. Like take something you like from your favorite class. Like if that's statistical mechanics, then simulate like a bunch of particles, each with their own energy and interacting according to some rules. Or like if it's E&M, you might want to solve like Poisson's equation and solve for like the voltage everywhere in a 3D space. So that's like finite element type solving. Or you can take an experimental device and see what it would do in the real world. Say, okay, this is going to have like, if I give it this input, it's going to have this output, but with this much uncertainty from like experimental, like just real life being sad sometimes. So one like really cool one that I've done a bit of is optical propagation through lenses and mirrors. Of the action of a lens, for example, is not like perfect one-to-one. You're going to have some distortion. Can you characterize that distortion? What does it mean for like if I'm imaging an object, how much does that distort like if you see a transit or not on an exoplanet? So there's connections here to like some really big like almost open questions in these fields. But yeah, pick your favorite experimental device, make like a code representation of what it does, and see what you find. Or you can pick one of the packages we showed you or something else and learn it and say my project was to learn this package and I produced these examples. That's also valid. And depending on what you want to do after this in terms of research, that may help you. Okay. Another option is something you're doing already. So a reminder of our policy from the very start is if you're already doing something that needs coding, if you're involved in research already, if you're taking a class that has some coding in it, if you're doing something for a club, you can count it as your class project here under these like pretty light restrictions. It needs to be somewhat relevant to something we've talked about in class, which is like, we'll be pretty generous about that, but just it can't be like, you need a slightly stronger connection than it has code in it, but not that much stronger. It needs to have documentation, which is very important, and we'll cover what we need for that close to the time. And in the documentation lecture, of course. It needs to have version control history, which is what next week's lecture is about. And if it's for another class, then you do need the permission of the other instructor to use it for this. I wouldn't imagine that would be like a serious problem, but we just want to make sure we're above board. Okay. So those are the things we can do. Now let's proceed to open discussion. And I'm going to check all these chat messages. I'm going to end the recording at this point.